Let's wait for a couple of more minutes and then we will start today's discussion. Okay, let's begin today's discussion. Hi everyone. So myself, Prerak, and I will be taking this session. Okay, this is the fourth session in a row, and this is for the NPTEL course and invitation to topology. So, so what's the plan? Plan is I will I will write questions. I will give solutions to them, and I will leave a few exercises in between. Okay, and in any at any point of time, if you have any question, you can unmute yourself and ask question, or you can raise your hand, or you can directly ask question in the chat, whatever suits you. Okay, and I will be happy to answer that. Other than this, if you have any other doubt from the first 4 weeks of the question from this course, you can also ask that as well. Okay, and I will try to answer that as well. So with that being said, um, we can start now. And once again, thank you for joining. Okay, so the first question is, yeah, one more thing, the recording of these sessions will be available on a YouTube channel. So my YouTube channel name is, if you search maths with Prerak Deep on YouTube, you will find my channel and you will find the previous recording of these live sessions as well. Okay. Moving on. Question number one. Which of the which of the following are closed sets? Okay. Option A, an arbitrary subset y of x with the discrete topology on x. Okay. Option B is the subset close 0 open 1 of y. So y is a subspace, y has the subspace topology, from the standard topology on R. Okay, this is option B. Option C is the subset singleton half of with R with RK topology. Okay, so this script R with K in the subscript is the RK topology on R. Okay, option D is the subset 1 comma 2 open subset times a closed interval in R2. Okay, and R2 with the product topology on R, with the product topology. Okay, so for those who joined just now, so this is another live session, and we will be discussing a few problems from the assignment 4. Okay, and now the first question is, which of the following sets are closed sets? Option A, an arbitrary subset X, an arbitrary subset Y of X with the discrete topology on X. So let me first let me first recall what do we mean by a closed set. So recall that uh, a a subset of X is closed if its complement, which is defined to be X minus A, is open in X in the topological space X tau. Okay, so that is what the closed that's what the closed subset mean, right? Now, what do you think about option A? Is a closed set? Option A, the arbitrary subset, any arbitrary subset of Y is a closed set in the discrete topology. You guys can answer in chat or by unmuting yourself, whatever suits you. So what is a discrete topology? Discrete topology is every subset of X is an open subset in discrete topology. Okay. Uh, so you just need to check that whether if you take any arbitrary subsets of Y, yeah, good. So A is true, and the reason behind that, you need to check that if we take any arbitrary subset Y of X with the discrete topology, then you need to say that its complement, which is X minus Y, is open. Okay, but in discrete topology, every subset is open. Every subset uh, in discrete topology is open. That is why the definition of discrete topology. Okay, so this will imply that Y complement C, which is a subset of X, is also open. Okay, so this is equivalent statement saying that this Y is closed is equivalent to say that the complement is open, and we know that it is open, so it is true. So good. What about option B? So option B says that this subset of Y. Now Y has a subspace topology from R. So now is this subset open in Y? Okay. So basically we are looking for the subset this in Y. So is it open? Is it closed? Is this subset closed in Y? That is what the question is. Again, you need to check that the complement of this in Y. Okay. So complement of this subset in Y. So which is this. Now what is Y? Y is mm, Y is this interval union with the singleton 3. Okay. So you remove this interval from, you are removing from this interval from this, so what you get, you will get, you will be left with 3. So the complement of this interval in y is 3. Okay. And now the question translates to, is singleton 3 open in y? Okay. So now question is being translated to this thing. So if it is open in y, then your original subset will be closed. Now how do we check whether a set is open or not? You need to say that whether it belongs to the topology of that particular space, the given topology on that space. So now what is the topology on 3? Now what is the topology on y? Y has a subspace topology on it, right? So can you find out a subset, a open subset in R, such that this singleton 3 is the intersection of that open subset in R with Y? Okay, then we will say that Y 3 is open in subspace topology. Okay, so let me write that down. So is there an open set in R such that open set U in R such that U intersection Y is 3, because Y has subspace topology and this is equivalent to ask to that. Okay, you guys can answer. So what topology does R has? R has a standard topology, and what are the basis of that standard topology? Or so an interval, open interval is a basis of that standard topology. So you can take uh, this set which is 2 comma 4. Okay, so clearly this is an open set in R. Okay, so Kamal, this is the fourth week going on. You might have, the registration might be open for the course, like registration will be open for a longer period, uh, but this is the fourth week going on, so I will be doing according to that only. You can, what you can do, you can go to the YouTube lectures, the YouTube channel that I just uh, told in the beginning, and then you can have a look at the previous sections, recordings of the previous session, and you can go through the lecture notes also first. No, it's not 22nd February, it's 22nd January. It's already been a month. Yeah, no problem. Uh, okay, so where I was, yeah. So you can take so this interval 2 comma 4 is an open interval in R. Okay, and if you intersect this interval with Y, now what is your Y? Y is this space. So if you intersect this, you can clearly see that the only intersected part is 3, is the singleton 3. Okay, you will get singleton 3 in the intersection. So this implies that 3 is open in Y, in the subspace topology on Y. Okay, and since 3 is open in subspace topology on Y, so its complement in Y will be closed. So that means this interval close 0 open 1 is closed in Y. Okay, is this clear to you guys? Good. Okay, now let's see this question. This option C. So you need to say that this singleton half subset, is this singleton half closed in R with Rk, where Rk denotes the K topology on R. So is this closed in this? Again, you need to check that its complement is open or not. Okay. Uh, yeah. So you can quickly tell me what it is. It is simple. It is not very tough. So it is also closed because the of half in complement of half is nothing but minus infinity to half union with half to infinity, right? So it is union of these two sets, and now each of this set is open in Rk. Why? Because you can write both of them as the union of these open intervals. Now this is an open interval. This is an open interval in Rk topology, right? Similarly, you can also write this as the union of these open intervals. Okay, so because these are nothing but the open intervals, union of open intervals, so each of this set is open. So this is open, this is also open. Since both of them are open, so it is nothing but union of two open set. So this is open. The complement of half is open. Okay. Um, so this is also closed in the RK topology. Okay. Um, so Kamal saying something. Hmm. So actually, this is not the classes, right? So you will find the actual lectures in the NPTEL portal. Okay. So what I'm doing is I'm just taking a helping session. Okay, where I will discuss a few problems from the assignment. I'm not going to teach you anything. Okay. So the teaching part has already been there on the NPTEL as lecture in lecture forms. Okay. So you log into your NPTEL portal, you will find lectures over there. There are week wise lectures. Okay. And you will get the um, lectures, the teaching by the professor in that portal. Okay, on Sunday I conduct these live sessions, okay, where I discuss a few problems based on the assignment. Okay, that's all. And you may also ask any doubt that you might have gone through in that week course, in that week's lectures note. You can ask me that as well. Okay, so I'm not teaching you anything new. It's already been there on the NPTEL portal. I'm more or less helping you out with the with solving problems and all. I hope that answers. And if you are asking for the recording sessions, yes, it has been 4 weeks only, and I have this is the fourth week going on. So I have three recorded sessions, and those three sessions are available on the YouTube channel of my YouTube channel. So you can go through that. But I will suggest first go through the lectures in NPTEL portal, and then you can also go through the so lectures are in detail. Okay, my discussion sessions are not in detail. Uh, they are very selective in nature. Okay, it those are on NPTEL portal. You must have registered somewhere, right? So you will get some link to the NPTEL course, and you can go there and you can find lectures over there. Right, right. That SWAM application. Right. Wherever you registered yourself, you go there. You will find lectures as well. Okay. 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 So now let's move on to option D. So in this option, you have given this set. Okay. We have given this product of two sets. Now in R2 topology, you need to say whether it is closed or not. Right. Um, so yeah. What do you think? What do you guess? Whether will it be closed or will it be open or none? Basically, you need to say whether it's open, whether it's closed or not in the product topology. Any guess? No guess. Not closed. Good. It's not closed. And why do you think so? Because you can notice here that there is an open factor. Okay. There is a factor of open set coming in the picture, and another factor is closed in R. So that's what make it non-closed. And now let's see the precise argument to say that. So if you want to say that something is closed, okay, if you want to say that this set is closed in the product topology, you need to say this is equivalent to say that um, the complement of this set is open in R2, right? Now what is the complement? Now you can write this complement. So yeah, this complement is open in R2. Now you can write this complement as, yes, R minus 1 comma 2 times 0 comma 1 intersection with 1 comma 2 times r minus 0 comma 1. Okay, you can rewrite it as like this, right? And now right? And now this complement, because if we want to say that this is open in R2, we need to say that this is nothing but product of two open sets in U cross V. Okay, where U and V are open in R, right? This is what we need to say. Okay, so now complement of this in R2 will be equal to F, right? Where will be equal to our original slide set. Okay. Now what is this? This product is nothing but R minus U, R minus U times V intersection with U times R minus V. Or we can also rewrite it as that if you have, let's say this is your U and this is your V, then V cross U will look like this, right? This is your V cross U. This will how it look like. And now if you look at the complement, so complement must be this whole part. So how do you write it as? You can write it as U complement. So U complement will give you this part times V complement. Now V complement will give you this part. So if you product these two, you will get you will get yeah. So this won't be part of. So you will get this outside of this thing. Okay. Now you want to include this part as well. So what is this? This part is union with. So what is this part? This part is the union of uh, yeah. So this part is uh, V sorry U complement times V, right? Uh, yeah, and union with U complement times V, right? So this is what you will get. Okay, so yeah, if I use this definition in the openness, so let's come back. So okay, let me up this whole part. So you can write R minus 1 comma 2 times an interval as, sorry, R2 minus this product as, think of it as U and think of it as V. Okay, don't think of as the open U and V. Think of it as product of two subsets. Now what will you get? You will get U complement, V complement. So which will be half complement times this complement, this whole product union with 1 comma 2 open intervals times V complement, which is this complement union with mm, yeah, union with the 1 comma 2 complement times 1 comma uh, 0 comma 1 interval, right? Now this set is what r minus this interval times r minus this interval. So this is neither open nor closed. So this is closed interval times an open interval, right? So this is neither open nor closed. Now what about this set? This is this is going to be open because this is open times open interval. So this is open, and this one is going to be closed. So it is union of mixed sets. Okay. So this is not an open set. Okay. So this is not an open set in R2. Hence, this is not closed in your original space. Okay. I hope this argument is clear to you. There can be other ways to show that it's not closed. You can use the limiting definition that on the boundary of the first component, the boundary of the first component is not included. Okay. But there can be sequences that converges to that in this open interval, and that sequence can be generalized in can be seen in R2 as well. So limit points are not included in this set, so it is not closed. That can be the other argument. But I hope so. This is a simpler argument, and this argument makes sense. Okay, let's now move on to a new question. Okay. Question number two. It says that um, RL be the set of real numbers with lower limit topology. Then which of the following subsets of RL are closed? A, Q, B, singleton 0, C, R minus Q, D, this interval. Okay. So I will give you a few minutes to think about this question, and then I will give a solution to this question. And just to recall, what is a lower limit topology? So RL is basis of RL are given by these sets. Okay. Okay, let me discuss this solution now. So R is the set of topology with a lower limit where the subsets look intervals looks like this are the basis that generates the topology R. Okay. Now let us look at option A. So Q is a set of our rationals, and we know that Q are dense. Q is a dense subset of R. Okay. And now, in order to say that it is closed, you need to look at the complement of this. So now, is this complement open? So now, what is the complement? Complement is nothing but the set of our irrational numbers. And in order to say that something is open, you need to say that every point in that subset is an interior set. Okay, is an interior point. So every p in this complement is an interior point. That is, there is an open interval. There is an open subset, or there is an open neighborhood. This contained there is an open neighborhood of P of this type contained inside the R minus Q, in order to say that it is an interior point. But you can notice that such interval won't be part of R minus Q, because A and B, because this interval, uh, but since Q intersects with this is non-empty, okay, for any AB in R, we get that P is not an interior, and this is because the reason why Q can't have empty intersection with any interval of such kind, because Q is a dense set. Okay, so P is not an interior point, okay, of the set of our irrationals, and this will imply, and this implies that Q is not open in RL. Okay, is this argument clear to all of you? And the similar logic can be applied for option C. Now, similarly, R minus Q, which is nothing but Q, is not open. Okay, and Q is also not open in nature because it doesn't contain intervals of such kind. Okay, it will have non-empty intersection with it, but it doesn't contain a complete interval in it. Okay, because there will be irrational points sitting in this interval, right? So this is not open, and this implies that R minus Q is also not closed. So option C and A are not the answers. What about B and D? Let's explore that. Okay. So what about B and D? So I would ask again, like, what is your guess about option B and D? What about option B? Will that be a closed subset? And what about option D? Will that be a closed subset as well? Yes, B is correct answer. B is, uh, and D is also. Okay, so let us look at why. So first, let us see why 0 is a closed in RL. So because if I look at the complement, its complement will look like minus infinity to 0 union with 0 to infinity, right? And now we need to say that both of them are open subsets of RL. Okay, now why is this open? Because you can rewrite it as a union of these intervals. Okay, now each of this interval is open in RL. So because this set open minus infinity to 0 open can be rewritten as the arbitrary union of countable union of basis elements in RL. So it is an open subset. Similarly, the other interval 0 to infinity can also be rewritten as um, yeah, 0 to infinity. How can we write that? Hmm, this can be written, yeah, this can be written as 1 over n to infinity. Okay. So now each of this subset is again open in RL, and it's a countable union of open set, so it is open in the RL topology. So because of that reason, Both of them are open subsets, hence the complement is open. So 0 is a closed set. Now let's look at the option D. Option D says this interval is open in RL. And why is that? Because if you look at the complement of this set, you will get minus infinity to 0 union with uh, 1 to infinity. Okay, so we already have seen that minus infinity to 0 is open set. This is an open set we have already seen. Now what about the other set? Now other set 1 to infinity can be rewritten as the union of 1 to n. Okay, and now each of this is open. So 1 to infinity is also an open subset in RL. And since the complement of this 1 to 0 to 1 is open, so it is a closed set. Sorry, it is a closed set. Now, since is open in RL, we get this is closed in RL. Okay, is this clear? Is this clear? Shall we move ahead? Okay, good. Okay, now let's discuss question number 3. So this question says that let x tau be a topological space and A is a subset, A be a non-empty subset of X, then which of the following are true? Okay, so option A is contained inside the A closure. Option B is A closure is a proper subset of A. Option C is if B is closed in X and A is a subset of B, then A closure is also a subset of B. Option D is if A is closed in X, then A closure is a subset of A. Okay. Again, I will give you a minute or two to think about this question, and then we will discuss the solutions. Okay, now let's the solution. Okay, A and D. That's what your guess is. Mm, actually, A, C, D are the correct answer. Only B is the wrong answer. Okay, so option A is trivial. Option A is trivial because A is already a subset of A closure by the definition of A closure. So A closure is what? Let's us recall that it is A union with the limit points of A. Okay. A closure is nothing but A union with the set of all limit points of A. Now, what is the limit point? Limit point of A. So P in X is said to be a limit point of A if every neighborhood U of P intersects non-trivially with A. Okay. So such a point is called a limit point. Okay. Um, so yeah, so this A closure already contains A. Okay, so it already contains A. So option A is correct. Option B is wrong because A closure has extra points in it, which are the limit points of A. Okay, so it can't be a proper subset of A. Proper subset means it needs to be properly included inside A. Okay, but A closure can be A closure is a larger set than A. Okay, so this is wrong. What about C? C says that B is closed in X and A is contained inside B. Okay, now when I say that B is closed, so B is closed. Okay, so when I say B is closed, I also mean that B is equal to its closure. Okay, this is an equivalent definition of B being closed. So B is equal to its closure. Okay, so with that said, um, B, that means all the limit points. So let us denote this set by a prime of that subset. Okay, so B prime, the set of all limit points, already contained inside B. Okay, they are already part of B. uh, and A is a subset of B, right? So whatever limit points of A, that will also be part of the limit points of B, right? And uh, we know that B prime is a subset of B. Okay, so this implies that A prime is also a subset of B. So A is a subset of B and A prime is a subset of B. So this implies that A union A prime is also a subset of B, which is A closure is a subset of B. Okay, so C is also true. Was that argument clear? This is the argument for B. Sorry, this is the argument for C. Is this clear? And similarly, option D, which says that A is a closed set in X, then A closure is contained in A. So I just use this equivalent definition. So which says that B is closed if and only if its closure is equal to itself. Okay, and that's what the option D says. So what does this mean? This is equivalent to say that B closure is a subset of B and B is a subset of B closure. So this is the option that is what given in D. So D option is also correct. Okay, so A, C, D is the are the right answers. A, C, D are the right answers. Okay, good. Now let's discuss question number 4. So question number 4 says, let X be let X be a non-empty set with the discrete topology, and Y be a subset of X, then Y closure is option A Y, option B X, option C empty, option D X minus 5. Okay. So again, I will give you a minute to think about this question and then we will discuss the solution. So X be a non-empty set with the discrete topology and Y is an arbitrary subset of X. Then what can you say about the closure of Y? Is it going to be Y? Is it going to be X? Is it going to be empty set? Or is it going to be the difference, the complement of Y basically? Okay, so yeah, so we have already seen today that any arbitrary subset of a discrete topology is closed. Okay, and it is also open in nature by definition. Okay, so any subset, any subset Y of X in discrete topology is open. Okay, this is by definition. And any subset in discrete topology is closed also because its complement is again going to be open. Okay, so any subset of X is open and closed both. Okay, So because of that, since Y is closed set, its closure will be Y itself. Okay. So option A will be the correct answer in this case. Right? Is this clear? Okay. Let's move on to question number 5. Question number 5 says that let X be an infinite set with all set with finite complement topology, and U be a subset of X, then which of the following are true? Okay. Option A, if U is a finite set, if U is finite, then U closure is equal to, then U is equal to its closure. Option B, if U is infinite, then U is equal to its closure. Option C, if U is infinite again, then U is equal to X. U closure is equal to X. Option D, if U is finite, then its closure is equal to X. Okay. Is the question clear? Okay. Um, so now let's discuss the solution. So X be an infinite set with finite complement topology. Now what do we, let us first recall what is finite complement topology. So finite complement topology, let me write it as tau fc, said to be all subset in X are open if its complement is a finite set. Okay. So uh, every subset whose complement is finite is an open set in this topology. Okay. So now option A. Option A says that U is a finite set. So if U is finite, what does this mean? That its complement is open. Okay, its complement will be open. So this implies that U is a closed set. Okay, so U is a closed set. So, and we know that for closed set, the closure of the closed set is itself. So U closure is equal to U. Okay. Similarly, for option B says that U is infinite, then its closure will be itself. So now if U is infinite, we can't say anything about its complement. Okay. It could be a infinite set or it could be a finite set. Okay, we can't say anything about it. So then, in that case, let's call their complement to be V. Now, now what is yes? Okay. So let us look at this. So U is infinite subset, right? So U closure, and we already know that U is contained properly. U is contained inside its closure. Okay. U is a subset of U closure. So this implies, and we know this. So both of the fact implies that U closure is an infinite set, infinite subset of X, infinite closed subset of X. Okay, to be precise, because U closure is a closed subset. So it is a closed subset, it's an infinite closed subset of X. Okay, so U closure is an infinite closed subset of X. Now, what are the closed sets in X? So any closed set has any closed set C has complement to be open. Okay, so this will imply that, and what are the open sets? Open sets are those only in this finite complement topology whose complement is open, whose complement is finite. So this implies that C is a finite set, finite subset. So any closed set in this finite complement topology is a finite subset, except that C is X or empty. X expect except C is the whole space or empty set, right? So except whole space and empty set, if you take any proper subset which is closed in this finite complement topology, it has to be the finite set. Okay, right. So because of this fact, U closure is an infinite subset, infinite closed subset of X, because it contains U in it, which is an infinite set. So this will imply that U closure has to be X itself, because X is the only infinite closed subset of X. Okay, this is because X is only infinite closed subset of X with the finite complement topology. Okay, so this will yeah, so X closure, so U closure is equal to U. This is wrong. Okay, this is wrong, but option C is correct. So option C is correct. Okay, so this explains option B and C altogether. And D is also wrong because the explanation that I just gave for A. Okay, so option B, sorry, A and C are correct, and B and D are wrong. Okay, is this question clear to all of you? Is the explanation for B was clear? Okay, now let's move on to discuss question 6. Right. So we have considered the metric topology, tau on R2 given by the following. Given by the following metric D. Okay. So this is a metric given on R4 to such that for x is equal to x1 comma x2 and y is equal to y1 comma y2, such that d of x comma y is equal to x1 minus y1, x2 minus y2. Okay. Now note here that each of xi, yi both are belongs uh, to 2. Xi and yi both are belongs to R2. Okay. So this norm is an R2 norm. Okay. This needs to be noticed. Okay. Now question is, this is a given set of all xy in R2 whose distance, yeah, so this is the metric on R2, right? So now this is a subset of R2 Now the question is about what is the complement of, sorry, what is the closure of this? So this is the question. What is the closure of this thing? How does the closure of this look like? Uh, so this is not the question. So the question is which of the following option, which of the following point belongs to the closure of the set? Option C is half comma half. Option D is 1 comma 0. So okay. I hope the question is clear. Okay. So I will again give a few minutes to think about the question and then we will discuss the. Okay, now let's discuss the solution of this problem as well. So, so here is one thing to notice, that is earlier also I said that x1 and x2 are so xi's and yi's are points in R2, and the metric that is given, the difference on the difference of x1 minus x y1. So if you do the difference, you will get a point in R2 again. Okay, and the length of that point is given by the metric, the norm on R2. So this is not the metric, this is basically the norm on R2. And how do you define a norm in R2? So norm on R2 is given a point a comma b. Norm of this is nothing but a square plus a square plus uh, no, not the a square plus b square. It is nothing but a minus b whole square. Okay, so now let us look at the yeah. Now let us look at the set. So condition given, that is this. So what is this now? So x1 is x, y1 is y, x2 is 0. Sorry, x1 x2 are x1 y1, and y1 y2 are 0. So x1 minus 0 plus x2 minus 0. So we'll get mod of x plus mod of y. Both are norm in x and y. So you will get x square plus y square. Okay, and if you put it back into the condition, so you will get set of all x y in R2 such that x square plus y square is smaller than equal to 1. Now what is this? This is precisely the disk. So notice that a is a unit radius open disk in R2. Okay, unit radius open disk centered at origin in R2. Okay, so now what will be the closure? So closure of this will be the set of all points. Basically, the boundary of the disk will be the closure of this set. So it will be precisely the closure will be is equal to 1. X square plus y square is equal to 1. So the circle will be the boundary. Okay. And now you can okay, sorry, this union A. So this will be the closure. So this will be the limit set, limit points, and this will be the entire set also needs to be included. So A closure will be this. Okay, now I just need to see that which of the points belongs to this disk. Okay, so option A was 0 comma 0. So 0 comma 0 clearly satisfies this equation, and it is already part of this. So you can further write the equation for this A closure. So A closure will be just nothing but set of all points in xy such that x square plus y square is smaller than equal to 1. Okay, now you can check which of the points belongs to this set. Okay, so 0 comma 0 already belongs to this, so it is part of the closure. Similarly 1 comma 1, this is also part of the closure. Sorry, 1 comma 1 is not the part of the closure, because 1 plus 1 is equal to 2, and 2 is not smaller than equal to 1, so it is not part of the closure. Half comma half is part of the closure, because half square is 1 by 4 plus 1 by 4, and this is smaller than half. Okay, similarly 1 comma 0 is also part of the closure, because 1 plus 1 square is 1 and plus 0, this is smaller than 1, so it is also part of the thing. So except C, everyone is part of this closure. Except B, everyone is part of the closure. So this is the answer. Is this solution clear to everyone? Okay, now let us discuss question number 8. It says that, mm, yes, so R is the notation for R with standard topology on it, and RL is the notation for R with lower limit topology on it. Okay, now the question is, which of the following are continuous? Okay, option A, function from R to RL defined by fx is equal to x. Option B, f r to RL defined by fx is equal to 0. Option C, function from RL to R defined by this. Option D, function from RL to R defined by the lower limit of x. Okay, so this is nothing but the largest integer less than or equal to x. Okay, so again I will wait for a couple of minutes and then we will discuss the solution. Okay, let me discuss this question now. So, uh, option A, f is a function from R to RL with which is the identity function. Okay, so now we need to say whether it is continuous or not. So, what is a continuous function? Image. So, image of of every open set U. Sorry. So we say f from R to RL or from X to Y. Let's use some generic notation. From X to Y is open if every open set U in Y, f inverse of U in X is open. Okay. So then we say such a function, sorry, we said such function to be continuous, my bad, if these conditions true. Okay, that's all we need to check. So first we have a identity function on A. So now let's take an open set which is, let's take 0 comma 1. So I'm discussing option A. So let's take open this interval which is open in RL. So this is open in RL. Okay, if you take pre-image of this thing, this interval, you will get back the same interval. Why? Because we f is a identity map, but this set is not open in the standard topology of R. Okay, so this is an, so this proves that f is not continuous. So f is not continuous function. Okay, so now look at option B. So f is a constant function 0. Okay, so given any open set U in RL, if you consider pre-image of U, it will be either empty or whole of R. Why? Because it will be empty if U does not, if 0 does not belongs to U, and it will be R if it belongs to U, because it is a constant function. Okay, and in both of the cases, in both of the cases, since phi and R are open set in the standard topology, f is continuous function. In both of the cases, we get an open set in the pre-image, so f is continuous. Okay, now let's discuss option C. So option C says, so B is continuous, right? Now option C is again a identity map, but defined from RL to R. So f is a function from RL to R, and f of x is x. So f is an identity function. Now we know that standard topology on R is finer than the lower limit topology. Okay, that's what we know. So that means if I can prove that given any, since we know that standard topology on R is generated by any topology on R, any topology is generated by its basis, right? So generated by, and what are the basis of this open topology? The basis, sorry, of this standard topology, the bases are precisely this. So these are the bases. Okay, right? The open intervals are the basis. So if we can prove, so does any open set is any open set U is an arbitrary union of these intervals, right? Will be an arbitrary union of these intervals or finite intersection of these intervals. Or so we only need to, so thus uh, so we only need to look at the pre-images of these intervals, right? And prove that or show that these pre-images are open in RL, right? And since we are working with the identity map, now since f of x is x, we get f pre-image of this open interval to be the open interval itself. And this open interval is open in RL because of the because this because RL is finer than R. Okay, so this proves that f is continuous. Okay, so option C is continuous. Now option D also. So I leave this as an exercise for option for you guys to think about what will happen to option D. And option D will also be an um, continuous map. Okay, so this will also be a continuous map. The pre-images of the integers over here will be the precisely the basis element of this thing. Okay, so given any point P here, uh, right? So you can first of all see that the images of this map are going to be integers. Sorry, the integers. Okay, if it is not the integer, then accept any point in the integer. So for D, I will give you some hint to think about. So D. So first thing to notice is that the image of F is set of integers. Okay, and pre-image of any point, if P is not integer, then pre-image of any point will be empty, right? So which is will be empty set. Okay, so and pre-image of any integer will be what? For n to be in this, you will get this interval, which is going to be n to n plus 1. You will get this interval, okay, for any pre-image of the natural number, and which is open. This is open. So if you take any open set in R, so precisely if you take any interval in R, so it will, so that interval may have more than one open sets in it. So this interval may have n1 up to nk uh, many integers in it. Okay, so you can draw this thing. So let's say this is a comma b, this is a comma b, and it has n1 up to nk many integers in it. If you look at the pre-images of this interval, so you will get an open set. So it will be union of these open sets, pre-images. Okay, and before n1 you will get empty, and after nk you will get empty. Pre-image will be empty, so it will be nothing but union of open sets. So it will be an open set. Okay. And it will be enough to look at the basis, the images of the basis only. So I leave this as an exercise. I have given you the rough sketch of the proof, and this will also be continuous map. Okay. So any question? If there are no questions, then we can stop here. We will meet next week. And thank you guys for joining. Okay.